section, we're going to talk about colligative properties. And colligative properties are interesting in that they depend on the amount or concentration of solute, but they don't depend on the identity of the solute. So colligative properties would have the same effect with sugar water or salt water or whatever if the amount or / concentration of particles in solution is the same. And two of the colligative properties that we're going to talk about are boiling point elevation and freezing point depression. And because these involve a temperature change, and we again need concentration, molarity is not a good unit of concentration. So molarity again is moles of solute per liter of solution. Instead, we need to use molality. And molality is moles of solute per kilogram of solvent. Why is this the case? Well, if you're looking at temperature changes, the liters of solution can change. Volume is actually temperature dependent, but mass is not. So if we use molality, okay, this new unit of concentration, which is very similar to molarity, it even has a similar name, we end up with a unit that is not temperature dependent. So the first thing that we want to do is an example where we actually calculate the molarity of something. So I'm going to put the screen back up over here. It says calculate the molality, not the molarity, calculate the molality of a solution formed by dissolving 19.2 grams of LiF in 250 grams of water. So if you'll recall from before, molality is equal to moles of solute per kilogram of solvent. Now we could convert grams to moles and then convert this grams to kilograms and plug in both, or we could do this like a dimensional analysis problem. To do it like a dimensional analysis problem, I want to go from grams of LiF to moles of LiF, and then I want to divide those moles by kilograms of solvent, and when I do that, I will get molality. So if you've seen me solve a molarity problem before, I do it the same way. So it looks more like dimensional analysis. It's technically not here because I divide instead of convert units, but it looks like dimensional analysis. So starting with 19.2 grams of LiF times, we need the molar mass on the bottom, so Li plus F, which is 25.94 grams of LiF on the bottom. On top, 1 mole of LiF times, to divide, we put a unitless 1 on the top. Now we can't plug in 250 grams because we need kilograms of solvent, so I have to divide that by 1,000, which is 0.2500 kilograms. And when we do all that math, we find that this is a 2.96 molal LiF solution. Again, as I mentioned before, molality will not change as temperature changes, but molarity will, because liters of solution will change. Cold water has a different volume than hot water. It turns out that for water at 4 degrees C, it has its highest volume. But there's a range in there, and the volume does change. The mass does not change, so we need to convert it into we need to use molality instead of molarity. We're not actually going to convert the two here. So if we look at the next slide here, if I can get back over to the slides, basically the second thing we need to consider is something called the Vant Hoff factor, because we talked about it before in the previous section about electrolytes, that when we dissolve ionic compounds in water, they actually break up into their component ions. So if we take KCl, it's going to have 2 ions in solution. And we determine, or we measure, I guess, the amount of species you find in solution as the Vant Hoff factor. So if we look at KCl, KCl breaks it into K plus and Cl minus, so the Vant Hoff factor is 2. Sodium carbonate, as we talked about in the previous section, breaks up into 2 sodiums and a carbonate. The polyatomic ions don't break up, they stay intact. So we have 2 sodiums and a carbonate. That's 1, 2, 3 species dissolved in solution. So the Vant Hoff factor is 3. Iron nitrate, it breaks up into an iron 3 plus and 3 nitrate. So 1 plus 3 is 4 total species. The Vant Hoff factor is 4. K2S, similar. We have 2K plus and an S2 minus, 1, 2, 3 species in solution, and the Vant Hoff factor is 3. And if we look at glucose here, okay, C6H12O6, this does not break up in water. Well, how do I know that? Well, this is a covalent compound. It does not contain a metal. So here, the Vant Hoff factor is 1. Every one of these I dissolve, I get one of these in solution. Versus for every one of these I dissolve, I get 2 things in solution. So I need to double it. Said another way, my Vant Hoff factor is 2. So if I look in the next example here, okay, and going back over to the sheet, we have what is the Vant Hoff factor for each of the following. And we have KNO3. And what I'm going to think about is I have KNO3 solid. What does this break up into? Well, it breaks up into K plus aqueous plus NO3 minus aqueous. Well, what's the Vant Hoff factor? There's 2 things in solution, so the Vant Hoff factor is 2. All right. If I have C6H12O6 solid, that becomes C6H12O6 aqueous. It doesn't break up because it's covalent when it dissolves in water. So the Vant Hoff factor here is 1. If I have potassium sulfate, it's going to break up into 2K plus aqueous and an SO4 2 minus aqueous. So there's 2 potassiums and a sulfate, so 1, 2, 3 total things. So the Vant Hoff factor here is 3. If I look at NaCl, so if I have NaCl solid, it breaks up into Na plus aqueous plus Cl minus aqueous, and that's 2 species in solution. So the Vant Hoff factor is 2. So essentially, in a colligative property, if something breaks up into 2 things, it's going to have double the effect. If it breaks up into 3 things, it's going to have triple the effect. Or if it doesn't break up because it's covalent, it's only going to have that effect, okay? Because remember, colligative properties depend on the amount of particles in solution or the concentration of particles in the solution, not on the actual nature of those particles. So it doesn't matter which one of these things I dissolve, it just matters how much. So if I look at my next example here, or excuse me, my next slide, okay, we're going to talk about boiling point elevation. And in the next couple of slides, we're going to talk about boiling point elevation and freezing point depression. But boiling point elevation is a little bit easier to understand. So if we look here in terms of the vapor pressure, okay, if we look at these molecules, and we talked about vapor pressure before in a previous chapter, vapor pressure is the pressure of the gas above a liquid. And if we look at these molecules at any given temperature, some of these molecules will have enough energy to fly into the gas phase. And the amount of molecules in the gas phase is measured by the pressure. And from the ideal gas law, PV equals nRT, the amount of molecules in the gas phase and the pressure of the molecules in the gas phase are related to each other. Okay, so for pure water, we have these molecules flying into the gas phase. But let's look at an aqueous solution. And in an aqueous solution, we have 2 things going on. First of all, these molecules are going to fly into the gas phase when they're at the surface. Because if they're not at the surface, they're going to bounce into other stuff before they fly out into the gas phase. So only a small portion of these molecules at room temperature will have enough energy to fly into the gas phase. If they don't happen to be right at the surface or very close to the surface, they're probably not going to make it all the way out before they lose some of that energy. Then let's look at, well, we put these ionic solute in here. 2 things happen. One is that the ions take up some of the surface. So this blocks water molecules from flying out. And another property that can also happen is there's some attractive force between these ions and these water molecules, okay, which causes them to be less likely to fly out. The major factor, I think, is that we have this surface being blocked by these ions or these solute particles. So what happens at the end of the day? Well, at the end of the day, we have more water molecules in the gas phase for the pure water and less for the salt water. Said another way, the vapor pressure of pure water is higher than the vapor pressure of salt water. Therefore, if we want to boil pure water, it will boil at a lower temperature. We have to add less energy for the average molecule to have enough energy to go into the gas phase for pure water than for salt water. And this is called boiling point elevation. If we were to look at a phase diagram and we were to look at pure water, okay, so we basically look at these phase change curves for pure water, we're actually going to have to increase the temperature it takes to boil when we have solute particles, in this case for salt water. And it turns out that we end up with a freezing point depression. We actually have to lower the temperature even more to freeze the water. And this explains why we put salt on the roads in the winter. When you put salt on the roads in the winter, the salt mixes with the water to form salt water. Salt water has a lower freezing point than pure water. So even if it's below freezing, the salt water may melt. Now this only works to an extent, right? If it's 10 below zero in Fahrenheit, you're probably not going to be able to melt. You're definitely not going to be able to melt the mixture of salt and snow. But if it's say 20 or 25 degrees Fahrenheit, the pure water will not melt, but the salt water may, which is why we put salt on the roads in the wintertime. So let's look at this from a mathematical perspective. We have two equations where that are very, very similar. This is called the boiling point elevation. This is called the freezing point depression. When it comes to the boiling point elevation, the change in the boiling point is I, the Vant Hoff factor, the number of particles in solution, times Kb, the boiling point elevation constant, which happens to be 0.5 degrees C per molal for water, times M, the molality, or the concentration. So basically, we take the concentration, we multiply it by the Vant Hoff factor, how many particles we get in solution, and we multiply it by a constant. The freezing point depression is the same thing, except we use the freezing point depression constant, which happens to be 1.86 degrees C per molal for water. So let's look at two ways that this question could be asked. The first way is looking at solutions with different solutes in them. It says choose the aqueous solution below with the lowest freezing point. And it tells us that they're non-volatile solutes, so they don't fly into the gas phase, and we're going to assume the ideal Vant Hoff factor. So if you recall from a second ago, we have delta T F, the freezing point depression, is equal to I, the Vant Hoff factor, Kf, the freezing point depression constant, times M, the molality, the concentration of the solution. Well, if you notice here, all of the molalities are the same. So Kf is a constant because they're all dissolved in water, and M is a constant because in this particular question, they made the molalities constant. So the freezing point depression is going to depend on the Vant Hoff factor I. So what we need to do is we need to determine the Vant Hoff factor for each of these different solutes. So KNO3 breaks up into K plus and NO3 minus, two different things, so I is equal to 2. If we look at glucose, C6H12O6, it doesn't break up at all in solution. It will stay as C6H12O6, so I is equal to 1, and that is because it is covalent. K2SO4 breaks up into two K pluses and SO4 2 minus, so 2 plus 1 more, a total of 3, so I is equal to 3. And NaCl breaks up into Na plus and Cl minus, so I equals 2. So the one with the lowest freezing point depression is actually going to be the one with the highest Vant Hoff factor. The change in temperature will be the greatest if this is 3 as opposed to if it is 2 or 1. So the answer here is the K2SO4 because it has the highest Vant Hoff factor. Another example of this that we can look at is where we actually do a calculation for the freezing point depression, as opposed to just look at it in that way. So in this case, it says calculate the molality of a solution when 0.981 grams of copper 2 chloride, and it gives us molar mass, is dissolved in 45 grams of water. What is the freezing point depression of the solution? And it gives us the Kf of water and asks us to assume the theoretical Vant Hoff factor. So here, just like before, delta T F equals I times Kf times M. So we need to figure out I and M in order to be able to solve this. Now the question asks us to figure out molality, but we were going to have to figure that out anyway. So let's do the molality first. So if we do this, we do grams of CuCl2 to moles of CuCl2. And then we take those moles and we divide by the kilograms of solvent, water, and this will give us the molality that we need to plug into this equation over here. So starting with the number of grams, which is 0.981 grams of CuCl2, times, we have the molar mass, we put that on the bottom, 134.45 grams of CuCl2, and on top 1 mole of CuCl2, times, now we want to put a unitless 1 on the top so we can divide by kilograms, and we need to convert these grams to kilograms. Said another way, we need to divide by 1,000, which is 0.0450 kilograms of water. When we do this math, we find that this is 0.162 molal. So this gives us molality. Kf again is a constant, so we can plug that in. What about I? Well, if we take CuCl2 solid, what does it break up into? It breaks up into Cu2 plus, aqueous, plus Cl minus, aqueous. And because there's 2 Cl's, we're going to get 2 Cl minus. So we have 1, 2, 3 total things. So I is equal to 3. That's the theoretical Vant factor. We can now do the math. Delta TF equals I, 3, times Kf, 1.86 degrees C per molal, times the molality, which we just found a second ago, which is 0.162 molal. And when we do all that work, we find that the freezing point depression, in this case, is 0.904 degrees C. So, we have now done a couple of examples where we've calculated freezing point depression. Now let's take a look at another colligative property, which is osmotic pressure. So in the case of osmotic pressure, we basically have a situation where we are going to have to think about this in this U-shaped tube, okay? Because it's the easiest thing to do. So there's a couple things to notice here. We have pure solvent represented by yellow dots here, and here we have a solution where the solvent is represented by the yellow dots and the purple dots represent the solvent, or the solute, sorry. So the solvent is the yellow dots, the solute is the purple dots. And then we have a semipermeable membrane. What does a semipermeable membrane do? Well, a semipermeable membrane allows the water to pass through, but it doesn't allow the solute to pass through. So what's going to happen in this case? Well, what happens is the water flows from low solute concentration, in this case no solute concentration, to high solute concentration. So the water moves across the membrane at the beginning in this direction more often than it moves in this direction. The reason for that is you could think of these solute particles as little magnets. So the solvent is attracted to them and it crosses over to be more attracted to them. A general way of thinking about this is nature tends to dilute. So the water molecules flow towards the higher concentration, thereby diluting the higher concentration on this side. But it turns out that this will not flow over here completely forever. Okay, you reach a point where it stops flowing, which is why we think of this in a U-shaped tube. The point at which it stops flowing, the solvent level, or whatever, the liquid level on this side goes up, and the liquid level on this side goes down. And the difference in height here is referred to as the osmotic pressure. So the osmotic pressure is not infinite. We can't just continually have solvent flow in this direction forever. It'll eventually reach an equilibrium where the rate of solvent flow in this direction and this direction become equal, and we can measure the height difference here as the osmotic pressure. So this leads us to, well, how can you do the opposite? right? And practically speaking, we're usually interested in doing the opposite. We want to take a solution like ocean water and turn it into drinkable water. Well, you could boil the water theoretically, and you could do that, or you could do reverse osmosis. And what reverse osmosis, and these are just two pictures, like a household one and a military application type one, or a larger scale one, these basically use pumps to increase the pressure on the solution here. And if you increase the pressure on this solution, it'll actually flow in the opposite direction through the semipermeable membrane, and you'll turn salt water, like seawater, for example, and turn it into pure water. Okay, now you might do this to the extreme, where you're actually using seawater, which is a pretty concentrated solution, or you might just make it, do it like to purify water in the chemistry building. We use a reverse osmosis system to do that as well, but we don't start with seawater to begin with. Okay, so this is how reverse osmosis basically works. It can also work in cells. It turns out that cell walls are semipermeable membranes that allow water to flow in and out, but are not allowing the solute to flow in and out. Now, to some extent, they will do that as well, but this isn't a biology course, so that's not what we're going to talk about here. Okay, so let's see what happens if we put cells into pure water. So the red blood cells contain about 0.93% sodium chloride. So if we were to put these red blood cells into pure water, which way would the water go? Well, the water flows from a low concentration, so pure water on the outside, into the cell where there's a higher concentration of salt. It turns out that if you put pure water here, you'll actually blow these cells up like a balloon, and they'll actually pop, okay? And this is called lysing or lysis, and also it's sometimes called hemolysis, okay? So you're self-lysing the cells basically by adding pure water. This is why if you give someone an IV, it can't be of pure water. It has to be of something that's isotonic, okay, 0.93% NaCl or 5% dextrose, glucose solution, things like this, okay? Isotonic solution, like I said, 0.93% NaCl or some other solution with the same osmotic pressure, the rate of water flow in and out of the cell is equal. So solutions that they would give in IVs would be these isotonic solutions. So water flows in and out, but the cells don't burst, they stay intact. You could also take these into a hypertonic solution, which is a solution which contains a higher concentration of salt, or a solution with a higher osmotic pressure. And when you do that, what's going to happen is the water is actually going to flow out of the cell, okay, and the cells will actually shrivel up as the water flows out. So osmosis is very important, not only to chemists, but also to biologists, okay? So let's look at an example here. It says red blood cells contain about 0.93% NaCl. When red blood cells are placed into a hypotonic solution, pure water, what will happen? Well, what will happen is the cells will actually blow up and can undergo hemolysis, all right? They'll swell up and they can explode and undergo hemolysis if it is pure water, okay? If the osmotic pressure is that different. The last thing we want to look at here in this section is how to actually calculate osmotic pressure. And osmotic pressure uses pi. Pi equals ICRT, okay? Where pi is the osmotic pressure in atmospheres, I is the Vant Hoff factor, C is the concentration in molarity, not molality. There's no temperature change here. R is the ideal gas law constant, and T is the temperature. And if you look at this, this looks an awful lot like PV equals nRT, except we changed this to pi instead of a P, and we added the I. Well, if we look at PV equals nRT and we rearrange it, we divide both sides by volume. If we take N over V, that's moles divided by liters. Well, what is moles divided by liters? That's molarity. So P equals mRT, or pi equals CRT. We change the concentration to a C, we change the pressure to a pi, and we add the Vant Hoff factor because the number of particles is what matters. That's in solution, so we have to have a correction factor for how many particles we get when we actually put the things into solution. So let's look at two examples where we actually solve this type of problem, and these two examples are similar, but there are different ways of asking it. So let me switch over here to the camera so we can go over these examples. It says, what is the osmotic pressure of 1.5 liters of solution containing 2.85 grams of NaCl at 25 degrees C? And it gives us the molar mass of NaCl. So in order to find the osmotic pressure, we need to use the equation pi equals ICRT. Okay, so a couple things. The temperature has to be in Kelvin. If you remember back to the ideal gas law chapter, temperature had to be in Kelvin. And R is a constant, 0.08206 liter atmospheres per mole K. But we don't know the concentration in molarity, and we don't know the Vant Hoff factor. So let's find the concentration in molarity first. To do that, we go from grams of NaCl to moles of NaCl, and then finally we take those moles, I did this in the last one, and we divide by the liters of solution. And moles over liters gives us the molarity. Okay, so starting with 2.85 grams of NaCl times, we put the molar mass on the bottom, 58.44 grams of NaCl goes on the bottom, 1 mole of NaCl goes on the top, times 1 over the volume of this solution in liters, which is already given in liters, 1.50 liters. And when we do all that math, we find that this is a 0.0325 molar NaCl solution. The only other thing we need to solve this problem is I. Well, if we have NaCl solid, it's going to break up into Na plus aqueous and Cl minus aqueous. So I is equal to 2. We can now plug in pi, okay, the osmotic pressure, equals I, which is 2, times the concentration, which is 0.325. Sorry, I made a mistake there. 0.0325 molar. R is a constant, 0.08206. That's liter atmospheres per mole K. Times the temperature has to be in K. So we can't add 25 here. We have to add 298 to, or excuse me, we have to add 273 to this, which gives us 298 K, the temperature. And when we do that, we find that the osmotic pressure of this solution is 1.59 atmospheres. Okay. A different way that this question could be asked is actually as a way to find molar mass. It says, what is the molar mass of a non-electrolyte compound when 14.1 grams are dissolved to make 2.35 liters of solution with an osmotic pressure of 0.541 atmospheres at 20 degrees Celsius. All right, so a couple things. First of all, we know it's a non-electrolyte, so therefore we know I is 1. Okay, only electrolytes are going to break up into their component ions in solution. The other thing we know is the mass of the solution, the mass of the compound, and then we know the osmotic pressure and the temperature and the volume. So we now need to make a calculation here in order to find the molar mass. Well, in order to do this, what we need to do is several steps. The first thing is pi equals ICRT. Well, in this case, my variable that I want to find is concentration. So I divide by IRT, and I find C equals pi over IRT. Well, I can plug in the osmotic pressure, 0.541 atmospheres, divided by I, which is the Vant Hoff factor. It's a non-electrolyte, so it's 1. R is 0.08206 liter atmospheres per mole K. And the temperature has to be in Kelvin, so 20 plus 273, which is 293 K. And I find the concentration is equal to 0.0225 molar. Okay, well, I could find concentration because that was the only thing I didn't know from my pi equals ICRT. But how am I going to convert that concentration into a molar mass? Well, I need to know two things in order to find molar mass. I need to find grams and moles. So molar mass is equal to grams divided by moles. Grams are relatively straightforward. They're given in the problem. Moles I need to find. Well, how am I going to find moles? Well, what I want to convert is my liters of solution to moles of solute. How do I convert from liters to moles? I use the molarity. So if I start with 2.35 liters of solution times what 0.0225 molar means is 0.0225 moles per liter. Per how many liters? 1 liter. So if I put 1 liter of solution on the bottom, okay, I could put 0.0225 moles of solute on the top. And when I do that dimensional analysis, multiply by the top, divide by the bottom, I find that there are 0.0529 moles of solute present. Now, to find the molar mass, I take the grams. Sorry, I should write that more clearly. Molar mass is equal to the grams, 14.1 grams, divided by the moles, 0.0529 moles. And when I do that math, I get that the molar mass is 267 grams per mole. So in this section, we learned about some colligative properties. Specifically, we learned about boiling point elevation and freezing point depression, which involve the Vant Hoff factor, the number of ions that dissolve into solution when something dissolves. And it involved the molality, which is the moles of solute per kilogram of solvent. Then we learned about osmotic pressure. And osmotic pressure is defined in the way as we went over in this problem here.